Welcome to ExplainerCast Episode 6. I'm your host, Dave Smith.
And this is Shane Swenson.
We have some explaining to do. Okay, today is the second part in a yet-to-be-discovered multi-part series about, I guess we would call this communication at a distance.
Yep.
It started last episode where we explained what the telegraph is, and not just the telegraph that everyone knows and loves that came to compose companies like Western Union and AT&T, but rather the pre-AT&T telegraph, the made of gigantic pieces of wood.
That's right.
It was visual. Many miles, big towers, miles apart from each other, with encoding and error correction and all kinds of interesting things. And then, of course, last episode we covered the electromagnetic telegraph, which required the discovery of both storage and transmission of electricity, as well as the idea of electromagnetism, the ability to move little pieces of metal up and down and make clicking sounds on things so that we could transmit stuff, which greatly increased the number of screaming monks that we could transmit. There's a little reference to the last episode as well.
Yep.
So now we find ourselves beyond that history, and in today's episode, we're going to go even further and learn what happened next in the world of telecommunications. But first, an astute listener from last episode called out a mathematical error that we committed in our last episode. Shane, do you want to tell us about the deep, deep shame that we encountered as a result of this error?
Absolutely. And this falls in the category of it's dangerous to do math in public. And
yes.
and so one of our esteemed listeners called us out on this, and he was absolutely right. So just to kind of recap the situation last episode, we talked about these towers that could, by moving a beam that was attached to a mast that had some arms on the end into different positions, and it could send us essentially represent a symbol that would then encode some part of a message that was seen by another tower, say 7 to 10 miles away. And then that second tower, after they saw the symbol, they would then move their apparatus to mimic that symbol, which would have the effect of relaying that message another 7 to 10 miles to the next tower. And so with enough of these towers in sequence, you could now send messages over very great distances. And we tried to compute how fast those messages were traveling, and we estimated that it would take maybe 30 seconds for each relay point to relay the symbol to the next tower. And so we said, okay, 2 towers per minute times 60 minutes per hour. And then we made this egregious error. We said 120, and we had a units problem. It should have been 120 towers per hour, but we said 120 miles per hour. And by we, I mean, I think I mean me.
Yeah, this shame is all on you.
That's right.
Shane. I definitely would not have committed this error, clearly.
Of course. And so
everyone knows it's 120 towers per hour. I mean, this is common knowledge.
I mean, that's definitely like in like the ISO standard book of units. So, but if we do take that and say, okay, I'm going to simplify it here. Let's say that those towers were 10 miles apart. If we're going 120 towers per hour, then we're going 1,200 miles per hour, which is really fast. I mean, now we're for sure going a lot faster than horses can gallop and so forth. And so, I mean, you could cover the entire, continent of Europe, within, a fraction of a day. Whereas in the past, that would have taken a long time to send messages. So thanks for calling us out on that. And it's probably just worth noting, one of our goals with this is to be, I guess, somewhat spontaneous and authentic. And maybe another way of putting that is we really don't do a lot of research or pre-scripting on this. And so we will make little mistakes like this. We hope you'll forgive us, and we'll try to come clean when we notice or when you tell us about them. So thanks for that.
That's right. When we notice or you notice.
That's right.
Yeah. Oh, thanks so much, Shane. That is so cool. Yeah, over 1,000 miles per hour, which I think is a pretty good estimate, is really quite remarkable, because I think we were talking about just barely faster than horses, or maybe 2x, 3x faster than horses. Now we're talking 30x faster than a horse. Yep.
And in fact, just occurred to me, that's faster than the speed of sound in air. So really quite remarkable.
Oh, that's interesting. Yeah, when you have a multi-mile transmission over optics, you can go a lot faster than sound. Like the difference really is pronounced at that distance.
Yep. Yeah, we just had a thunderstorm here yesterday, so I was talking with my kids about the kind of rule of thumb that when you see a lightning flash, you can start counting seconds. And, I think it's around 5 or 6 seconds is the time it takes for the sound to travel 1 mile. And so if you see the flash, you count 5 seconds, and then you hear the sound, that flash was roughly a mile away. And so it just does illustrate how much slower sound is traveling than light.
Yeah, incredible. Okay, thank you so much, Shane. I do think it is a really great call out that this podcast is all about sharing topics that we already know about. So we're not really doing research on this stuff. This is just stuff we happen to know, and I think that affords us to go. But by the way, we'll only choose topics that we know pretty well.
Yep.
This affords us simultaneously to go deep on things that we've accumulated knowledge on for many years, but also it means we're going to make fun little silly mistakes. And in fact, it is our promise to you that we will embed at least one intentional mistake every episode for you to find and report on.
There you go. Does it have to be intentional? I can guarantee there's at least one without intent. So,
okay, well, that just makes your job easier, I guess.
That's right.
Okay, so moving on to the second part in this multi-part to be discovered number of parts series on telecommunications. After the electromechanical telegraph, where are we going next here, Shane?
Yeah, and maybe let's just, in fact, I'd say let's go after the optical relay with the kind of semaphore line that was developed in Europe, and maybe we'll just quick recap the basis for the electromagnetic as well telegraph, because that'll then motivate the ways that it was improved on, really from its invention in the 1830s until present day. Again, this was driven off of some key physics discoveries in the late 1700s, early 1800s. We talked about Luigi Galvani, and he was the scientist over in Italy who was electrocuting dead frogs. And then his frenemy, Alessandro Volta, who figured out that you didn't actually need frogs, though that was quite fun, I'm sure. But you could replace the frog with some like salt water and some appropriately chosen types of wire. The key being you had to choose two different metals. And if you put these two different metals, like say copper and zinc, and you coupled them through like a jar of salt water, or later like a piece of paper soaked in salt water, or maybe some type of acid, then because they had different electrical potentials in that electrolyte interaction chemically, they would create this electrical potential where you could then move electrical current from one to the other if you connected a circuit across them. And so he invented the battery and really this controllable form of electricity. And then at that point, that became like the coolest thing to have in your science lab. And so everybody that was somebody was doing that. And the next big step forward was, I think it was in 1820, there was a Danish scientist named Hans Christian Ørsted who noticed that as he was interacting with this electrical flow through his wires, that he also had some magnetic compass needles, and he noticed that they would move when he had electrical current flowing nearby. So a wire near the compass needle, when a circuit was created and caused electricity to flow, the compass needle would deflect. And so he really is credited with discovering this relationship between electricity and magnetism, which up to that point were thought to be two separate phenomena. So then the next thing that happened was people realized that you could create different types of effects, and especially you could create a very powerful magnetic effect if you wound wire around a piece of metal and you created an electromagnet. So when current's flowing, it forms a magnet. When you disconnect current, it stops being a magnet. And now the cool thing to do was to make really big electromagnets and like lift really heavy things with them.
Mm-hmm.
And so that became like the next thing people did. But meanwhile, people like Samuel Finley Breese Morse and others looked at ways to connect these ideas together to build this communication technology that we now call the electromagnetic telegraph. And so Morse's construct was to make a very simple electrical circuit that had a battery and a switch, which he called the telegraph key, and electromagnet attached by a wire. And when you press the key, it would activate the electromagnet, which would then, initially, it would actually pull a pencil down onto a piece of paper tape that was scrolling past. And later, it would just cause it to tap onto what was called a sounder. So you could hear the action of the electromagnet being activated and deactivated. And so he then created a system where the transmitter is in one place with the telegraph key, and the sounder or the receiver is some distance away, could be up to a couple hundred miles in his initial form. And they would receive the message in the form of what we call Morse code, a series of dots and dashes transmitted over that distance. And since this was kind of an evolution of this idea of distant writing, this is also given the term telegraph, along with that original tower-based semaphore relay that was used in France. It's worth noting there were a couple other people making similar things. In England, there was a system that was developed that actually used 5 wires instead of 1 that Morse used. And as a result, you could send a more complicated signal. And so to transmit, you would pick a letter and you'd kind of set this apparatus that would send a different signal on each of the 5 wires. And then on the receive side, those wires would cause a set of compass needles to deflect, and they would point kind of on this little graph towards which letter of the alphabet you were sending. Whereas Morse's...
Whoa.
So that was...
Wait, was each wire influencing a single compass? So five compasses, 5 wires?
Yes. And I can't remember if they used all 5 all the time or if they kind of used subsets of them in this kind of grid layout. But the idea then was to transmit, you just had to like move this selector to which letter you wanted to send, and then that would turn on
that is so cool.
certain wires, turn off certain ones. And then on the receive side, they would just kind of point and you follow the lines and you read out the character. So a lot easier to use. But there was a problem with the practicality of this. And do you see what the problem was, Dave?
Well, I'm guessing it's 5 times more expensive than the wire, which is the big resource.
Yes, exactly. It's way more expensive. The wire was tremendously expensive at the time. And also, it was less reliable because you needed all 5 wires to work.
Yes. Mean time to failure.
That's right.
Multiplicative effect.
Times 5, roughly. Yeah.
Yeah. Really bad failure rate, I bet.
Yep. And in fact, this was still early days where they were learning even how to make an electronic system that would last and how to insulate it and protect it from rain and things like that. And so, as I understand it, they laid these systems out, and then not too long later, one of the 5 circuits would fail, and now they're down to 4, and they had to figure out how to make it work with 4. And then another one failed, they're down to 3, and so tick, tick, tick. Eventually they're down to 1 anyway.
Let's just figure this out with 1 wire.
That's right.
That's all we got left.
That's right. And so everybody kind of then arrived at this idea of what we would call serialization, which is to take your message and to make it so that you only have to have one piece of information at a time, and you reassemble those in time back into the characters or the message you're trying to send.
Yes.
And Morse, again, did this with what was called Morse code, dots and dashes as we would know them today. And there's a story about this that he, or maybe it was his business partner, a guy named Alfred Vail, who actually went to a print shop and looked at their type box, all the pieces of movable type that they had, and used that as a heuristic to determine what the most commonly used letters in English language were. So things like an E are super common, whereas like a Q or a Z are much less common. And then the Morse code assigned...
I heard a rumor that they actually referenced the Scrabble point system to determine this.
There you go. Yeah, the Scrabble point system would be a good way. Like, the number of points is like the number of dots and dashes you're going to end up needing to send that character. So,
yes.
And that's what they did, essentially, is they said, hey, the ones that we're going to use a lot, let's give them a very short sequence, like a single dot or a single dash or 2 dots, something that can be very quick in time because we're going to use it a lot. The idea was, well, then we'll move faster through the message. Infrequently used characters, we can afford a longer sequence. So it was a variable length encoding scheme per character, which still persists as Morse code.
So a little bit of complexity in terms of the ability to interpret it, but humans have basically no problem with that, right?
Exactly. Yeah, it turns out, again, they initially meant to inscribe this on paper, and they quickly found out that with a little bit of time listening to it, your brain could kind of learn it almost as a language. And so it seems like it uses some of the same kind of processing capabilities where it becomes very intuitive for people who spend a lot of time with it.
This user experience evolution is one of the coolest things I've ever heard, where the original designers designed one system. And literally a side effect of that system, which is the sound of the pen tapping on the paper,
Yep.
became the primary mode of communication, which it just blows my mind how it's like we built this thing to be intuitive and obvious, and then it turns out the intuitive and obvious one is actually not the most intuitive and obvious one, but rather this little side effect of it turns out to be the easier one.
Yeah.
Not even easier, just faster and more effective and more comfortable.
And cheaper.
But took more training, right?
Yep. And you don't have to keep loading it with paper. And
yes, and cheaper. Yes.
Yeah.
Oh, so cool.
And I feel like if you set out from the get-go to design such a system, you would never think, oh, I know. People will just be able to hear this tapping and they'll know what I'm saying.
Yes.
Like, I feel like that would have been it had to be discovered like serendipitously through practice.
Ah, so amazing. And so many, I think, ideas are like that. And we'll probably stumble upon more.
Yeah.
But it's so cool.
Yeah, I think it's a great engineering metaphor for how product development has to be iterative. You have to do discovery.
Yes.
And
you have to ship something. You have to put something into production.
Yep.
You can't just talk about it. You have to build it.
Exactly. Because, you'd never figure this out in the planning stage. And then when you look at why we talk about Morse code and we talk about this formulation of the telegraph and not the one that was popular in England, it's really because it was simple, usable, lowest cost. And so, again, you would have assumed you had all these other requirements, like I can't rely on trained operators, and I have to have this paper, so that they can look at it and they can't learn it in real time. And those requirements went away, and then this became the ubiquitous solution because of that simplicity. So, good lessons on product design.
Can we go back just a moment to the idea of multiple wires and one wire?
Mm-hmm.
So you mentioned how, and this is a little bit counterintuitive, I think, at least it would have been to me years ago, and maybe to many, that 5 wires is actually less reliable than 1, because you have 5 wires, each with a likelihood of failure.
Yep.
Call it some percentage, maybe 2%
Yep.
chance of failure over the next 10 years or something.
Yep.
But when you sum, or when you have 5 of them, then the chances that at least one wire will fail is much greater than 2%. And I won't make the mistake of doing the math in public, but I think it's the sum of all the individual percentages. So it's more like 10% or something.
Yeah, it turns out it's a little more, the math is a little bit more subtle than that. It's easier to compute the probability that none of them fail. So in your metaphor, and actually I'm going to change the numbers to make it easier.
So the probability that none fail is like 2% times 2% times 2% 5 times, right?
So the probability that they fail was 2% per year. And there's 2 assumptions. One, we're going to say that it's an independent assumption, which isn't always true, because like if they're all in one conduit, you might blow the whole thing. But let's assume they're independent. Right. Then for small probabilities, you can add as an approximation, but to compute the real probability in this case, you'd say, well, what I actually care about is what's the probability that all survive? And so the probability that each one survives individually would be 1 minus 2%, so 98%. And then the probability that all 5 survive if they're independent would be 98% raised to the 5th power. So 0.98 times 0.98. And if you do the math, when you're looking at small numbers, it's pretty close to the sum. But when you start to get to big probabilities or large entity counts,
failure rates,
exactly, then it
or both.
Then you have to do the math kind of the other way. And then if you don't have independence, then this also kind of goes out the window.
Yeah. They fail together.
But nevertheless, even let's make it more extreme, because this is probably, realistically, they probably had more like a 10 or 20% per year failure rate. And so if you have 5 of them, the probability that one of those 5 is going to fail in a given year is quite high. Again, if I was going to do the math in public, it'd be 0.8 to the 5th power is the probability that all survive.
Which is about 33%, according to my calculator.
Okay, thanks. Thanks for catching me up. So yeah, you have a 1, and so if you did the additive version on this, if you just want to do it, and you said, well, if I'm going to take 20% for each of them to fail, and you added that 5 times, you would actually say, well, I have a 100% probability of failure, but you don't. You have a 67% probability of failure. Mm-hmm. And so, nevertheless, it's still quite high. And so I think this is the counterintuitive thing with any type of system design, is if you add more parts to the system that could fail, and usually anything can fail, and your system requires all of them to keep working, you'll actually make the system less reliable.
Right.
On the other hand, if you add more parts to the system and your system can tolerate some of them failing, you might make it more reliable. So on the other extreme, if I have a system that has 5 wires but only needs one of them to work, now my probability of success is quite high because I can have up to 4 failures and still be operational.
Exactly, yeah. And this is the NASA approach, right? Like put 5 of everything.
Yeah, put 3 computers on the space shuttle and make sure 2 of them agree, and that way 1 could fail. If they all 3 had to agree, it would be less reliable. But with 2/3 agreeing, then it had a chance to be better.
Exactly. And I do think it's interesting that here let's talk about the natural world where these wires existed in. They were learning about things like insulation. Like you said before, they were learning about the effect of the ground and the earth and how propping them up on poles and running them long distances would help with the reliability. But they had not yet encountered the number one enemy, number one most lethal, let's call it the apex predator of cables. And that is, of course, the modern backhoe.
Exactly. Yes, or if it's undersea, it's the ship's anchor. But yes, depends on your environment.
Exactly.
Like sea backhoes. So yes, that's right.
Our primary job is cutting cables. Sometimes we deliver packages too.
Exactly. Or it was a couple of years ago, I think there was some video footage of, like, I forget if it was Google or Facebook. Somebody had an undersea cable and there were like sharks biting it. And
well, it's true. I'm now the apex predator of 2 food chains.
That's right. So yes, they had, I'm sure, plenty of other threats. Backhoes were probably early days, but they did lay these next to railroad tracks, and so trains derailing and other adjacent things could take them out too. Not to mention, I think there was probably a little sabotage from time to time when people were suspicious of what this new technology was doing in those wires. But probably rain, moisture, seeping into the insulation and causing the low quality wire to degrade further is probably one of the more common cases. I guess the next thing that's worth talking about is we've simplified the system down to this one wire. And last time we talked about how you have to make an electric circuit, you need a full loop, which would typically require 2 wires, but Morse and others figured out they could use the earth itself as one of the returns for that. So you're down to 1 wire. And you have these 2 telegraphers at either end. And once they're up to speed, they could communicate conversationally with, I think relatively quickly. I think I hear numbers like 30 to 50 words per minute, which probably pretty quick for this type of distance. It's a lot faster, what we would call baud rate or bit rate, than the big semaphore towers, that we figured could do maybe 2 symbols per minute, so 30 seconds per symbol. Here, if you're doing 30 words per minute, that's a word every 2 seconds. And so I'm doing math in public again. A typical word is considered to be like 5 characters in a space, so roughly 6 characters. So you're looking at about 3 characters per second. I would guess in Morse code, each of those characters is a few bits. And so you're looking at 10 to 30 bits per second. I'm going to make a big range there, so I have lots of safety on that.
It's pretty good. Yeah, exactly. Well played. Well played. There's 2 ways to be not wrong with math in public.
That's right. Just make a wide error range. And a number like 50 bits per second, or 50 baud kind of comes to my head. That sounds pretty fast, but again, maybe they could get up to that kind of speed.
Yeah, so 50 bits per second would be in lower baud rate than that, though, probably, right? Like a third of that for baud, given that it's a few bits per symbol.
So in this case,
or are you counting the bits as the symbol?
Yeah. So in this case, if I'm thinking of the bits as dots and dashes, and I guess you have dots, dashes, and spaces, and you have short and long spaces. So you kind of have 4 different symbols you're really working with. And I think actually original...
It's a quaternary system.
There you go. So 2 bits per symbol or something.
So a quabit.
Yeah. We're probably outside the area I thought deeply about here. So if we're gonna keep true to our statement that we talk about things we understand, I probably got to back away from that one.
And we can't start making up new units. Okay, I'll back off then.
No, making up new units is fine. It's more.
Oh, okay.
As long as you understand it when you make it up.
Can't guarantee that.
It can explain it. So then the next idea was, okay, human beings are going to kind of go about as fast as they can go, and they made some fancy telegraph switches so that you could like wiggle something back and forth instead of just pressing on and off. And the other thing you had to do, of course, is you couldn't go faster than the receiving operator was capable of hearing and discerning at. And so...
And let me just interject here, because unlike the wooden semaphore towers, which had a built-in acknowledgement system, the one-wire Morse code system, or any Morse code system, has no acknowledgement system, and apparently no error correction code either?
Yeah, not built into it. And so, in fact, the original Morse code, which is called the American Morse code, and most people today, if they learned Morse code, would have learned the International Morse code, which was an extension or an evolution of it. His original Morse code actually had the opposite of error correction. He chose to represent different characters with the same pattern of dots and dashes on the assumption that an English language speaking operator would be able to disambiguate it when they received it.
Whoa.
So,
okay.
I guess you could say he relied on the English language itself as his error correcting system.
Yes, which I guess does sort of have a built-in error correction system.
Yeah, there's actually...
And that's because it has a vocabulary.
That's right. I mean, we have a ton of error correction. Yeah, we have a vocabulary, we have a grammar, we have the assumption of semantic relevance, and we can talk about all that later and why modern language systems like text-to-speech and so forth do so much better than the ones that were developed 20 years ago when they didn't have the ability to leverage those things. So, but yeah, in the encoding scheme, no error correction. In fact, the opposite, which again, International Morse code said, at least let's give ourselves unique symbol patterns for every character. But you were still relying on the operators themselves to do any type of error correction or what we would call flow control. Basically to say, whoa, that was too fast. Could you please slow down? I didn't get it.
How would they do the flow control? Was there no way to do that?
So I think there's a certain amount of back and forth. Like you'd kind of take turns transmitting and receiving. And so when it was your turn to transmit back, you'd basically say, sorry, I didn't get that. Or, slow down. I think there were certain kind of phrases people would use to indicate. The other thing that I've read about is that a good operator would kind of hear the speed that the other side transmitted at, and they would sort of not transmit much faster than that. Like if I was very highly sophisticated, but I'm talking to someone who's going pretty slowly, I kind of assume that's maybe their pace, both send and receive. So there's kind of just some social negotiation.
Speaking of the social side, I just can't help but imagine how amazing it must have seemed to people who were experiencing this for the first time, having lived in a world where, let's say you're an older person, you've been on the planet for a good long time, you've never seen any kind of distance communication, and then you walk in a room where this machine just clicks and clicks and clicks, and the person that's making it click is literally thousands of miles away.
Yeah.
Which is totally reasonable, right? I mean, they could do this cross-continental, right?
Yeah, and I think maybe, to go that distance, they had relays, with fresh batteries and new wires so that they kind of rebuild the circuit. But for sure, like a couple 100 miles away, they could be on the other end of it, and maybe 1,000 miles away as well.
It just must have seemed so magical. I kind of wish I could have been there when the first clicking really worked at such great distance. The thrill would have just been off the charts.
I think so too. I think for people who understood it, and like a lot of technologies that show up, I forget who said it, any sufficiently sophisticated technology is indiscernible from magic. I think it would have just looked like magic to a lot of people.
Yeah.
And actually, there's other stories, like they started quickly trying to figure out, so Morse was developing this in like the 1830s. He did a big demo for the US government in 1844. Shortly thereafter, started these commercial ventures. And, by the 1850s, they were laying cable across the Atlantic Ocean between Newfoundland and England to build the first transatlantic telegraph. So now imagine you're overseas, which in the past meant put a message on a boat and hope the boat doesn't get lost and sink on the way. And
it was weeks, right? I mean, we're talking, 6 weeks to get across the ocean, best case?
I would assume, in that range. And then to get a response back. And then, of course, 1/3 of the time or something, they're never going to make it back. I mean, to now be able to send and receive information in real time had to just be mind-blowing. And so that was the first undersea cable that I know of for the transatlantic. But then the British, they had the British Empire around the world. They started laying cables across Europe, across oceans, like all the way down to India, through Indonesia to Australia, around to Hawaii, and back to like British Columbia. And they called this the Imperial Cable System. And they would have basically like telegraph parties where the elite, the aristocracy would all get together and they'd start sending messages to all over the world, and they get responses back in real time, and you can kind of picture this Victorian era party atmosphere where they're sending messages to people in these truly around the world. And yeah, it had to be quite the experience. One thing just to note on those, like the undersea cables, you couldn't send enough electrical current fast enough to reliably trigger the electromagnet. And so they did have other receivers for those cases that were super sensitive to very small changes in current. And so one of these was called a mirror galvanometer. And essentially it was a little mirror with a magnet attached to it, or a piece of magnetic metal suspended by thread with the electromagnetic coil adjacent to it, so that as the current flowed through that coil, it would just slightly change the angle of the mirror, cause it to rotate. And then they shined a light or a lantern at it, and it would reflect a spot some distance away, and you could watch the spot move. And that's how you measured the subtle electrical signal.
Oh my goodness. I can imagine that even with that subtlety, that sensitivity, wouldn't there be ambient electrical fields that would cause that to deflect?
Yeah, I imagine it had to be pretty isolated. And the other thing is it was pretty slow. So now your baud rate is going to be way lower, and you have to transmit very slowly, let it turn and settle long enough that the receiver can see it and say, this isn't an anomaly, this is a real thing, and then the next. And so your data rate went much lower as a function of distance, which is another kind of interesting, seems like fundamental information theoretic concept, that the farther you're going, often the slower you end up going.
And were these indeed the same mechanisms they needed to use to get across the ocean because there weren't relays in the middle?
Yeah, exactly. They didn't have a way to put another source of power under the sea. Some of the initial attempts to make the first undersea cable work, they just they didn't even know really what voltage was, but they just kept cranking it up to try to get a signal through, and they ended up basically burning up the cable, and it stopped working.
Yeah.
So then they laid another one, and then they figured out, we can't do that. We got to run it at a lower level of signal, which means it's going to be slower. We need this more subtle instrument to receive it.
Interesting that they burned the cable under the water, where it was undoubtedly very, very cooled. One might even say water cooled.
Yeah, that's right. Yeah. So I don't actually remember the exact failure mode, but I think just so much electrical potential, it might have actually shorted through the insulation to the seawater or something like that, and kind of fried itself.
Which then renders it useless. Yeah, that makes sense.
Yep. And so they definitely did what they could to optimize those use cases, both the short distance use case with human to human through the sounder, and then the long distance. I mean, they were just glad to get information over that distance, even if it did take longer, but of course at great expense. So kind of the next phase of optimization was back to that wire and the expense associated with that. And we've already established it'd be really nice if the two endpoints can communicate back and forth, and we would call this duplex communication. And the first formulation was half duplex, which means we can each communicate, but we have to take turns. And this is like when you're using a walkie-talkie or something, that's half duplex, right? You can hear.
Is that sometimes called simplex, or is that something else?
I think simplex might mean one way, like broadcast, receive, but you can't go the other way, but I'm not positive.
There you go. No, you're right. I actually did. I broke our rule and I looked it up.
Okay.
Simplex is unidirectional. Half duplex is two-way, one at a time.
That's right. Yeah, exactly. Sorry, real-time fact-checking there. So yeah, so
we allow ourselves one per episode.
Sounds good. We'll have to end soon then. So half duplex means we're going to share the same circuit, the same battery, the same wire, but we're each going to have a sounder on our side, and we'll take turns transmitting. And when I'm not transmitting, I have to keep my circuit closed so the current can flow through it, and then you can transmit by opening your circuit and transmitting. And then when you're done, you close your circuit, and then I'll open mine and I'll transmit. And so that works, but it means we have to do, just like on the walkie-talkies, we got to take turns. And if one transmitter goes too long, you can't say, hey, can you go back? I missed it, or slow down. So the next thing that you seek is what's called full duplex, which means, can I transmit and receive at the same time with you on the other end? And one option there is to have two wires. So we each have our own dedicated path. We each have our own battery, our own key. The other side has the sounder. But now we've just made
That's the expensive way.
Yeah, we made it twice as expensive. So we gained function at a cost. So it quickly became important to say, could we find a way to share that wire? And there were a few different people who worked on that problem, and they did figure out both how to share the wire for full duplex, but also how to further share that wire between two sets of operators. So, picture like we're in New York or something, and there's a lot of commerce, and we want to communicate rapidly about that from building to building. We could run two wires because we got more than one person's worth of traffic to send. But if they could share, we could actually now just double the capacity of the system with the wire that's already running through town. And so having two signals going at the same time was called duplex if it was one in each direction. Full duplex, having two signals going in each direction at the same time, the term given to that was quadruplexing. And this was actually invented by Thomas Alva Edison. As he was working on different types of projects, he developed a quadruplexing scheme. And this was, again, really one of those first commercial successes that gave him the funding to later go set up his lab where he developed all kinds of other things. And so we talked last time about how plex means place. And so duplex meant two things in one place. Quadruplexing means four things. In this case, these four signals in one place, meaning on that one wire.
So the four operators are a transmit and a receiver. And then in the same, essentially the same room, right? Is another transmitter and another receiver.
That's right.
And they can be clickety-clackety-clicking on their switches with no regard for the other person in the room. They can completely transmit independently from one another.
Yep.
How did they pull this off?
Yeah, they used some clever tricks where they chose. So the challenge with multiplexing is you have to figure out, well, what am I going to do that's unique about each of these? And so the first was
so just to add to that, so that the receive side can choose the signal that's intended for them and discard the other.
Yep, exactly. And in the quadruplexing thing, I actually have two different problems to solve. One of them is, let's just talk about full duplex on one wire. I want to hear your transmission, but I don't want to hear my own. I want you to hear mine. And so the way they did that...
And by the way, this is what happens when you join a video call, right?
That's right.
And you hear your own signal.
Yeah, you're echoing.
More specifically, your microphone hears your own signal and retransmits it over and over and over, which creates what we call a feedback loop, which is exactly the problem I think you're describing here.
Yes, and either a feedback loop or even just something like a really annoying echo. It's almost impossible as a human being to speak if you have an echo with like, a half-second delay or a 1 second delay.
Yes.
It just kills your brain. And so...
Yes, it does. We did not evolve to filter out our own voices.
Not at that latency. Yeah.
No, yeah, exactly.
So I want to transmit, but I don't want my sounder to click when I hit my key. And so the way that it might have been Edison, it might have been somebody else that solved that first was they played a trick, which was that they figured out how to make it so that essentially their signal would go to your end correctly, but on my end, I would basically cancel it out with a local copy. So I would get a kind of a copy of my signal that went to you and back, but I would cancel it out with essentially a local copy going kind of at the opposite polarity. So my electromagnet would not see any electrical current, even though yours would. And again, I don't have the whole circuit in my head. I don't want to probably go much farther than that, but that's a common technique.
But suffice it to say, it is a somewhat complex circuit of multiple components, all put together to make sure that your electromagnet doesn't hear what it's not supposed to hear.
That's right. And that basic idea.
And I actually pulled up a diagram of this, and it is pretty darn complicated.
Okay.
So this really was a worthy invention. It's not just, we'll just throw a resistor here, or it's like really complex mechanical switching and things like that.
Yeah, and I don't think today we have a pretty sophisticated understanding of electricity and electric circuits. I mean, back then it was still like one step past magic. And
yeah, exactly.
So it's like, try this. Does this work? No. Try something else. Does that work? Have
you tried using a frog's light? Because that worked the first time.
That's right. Just don't wire it backwards. Anyway, yeah. So that was the basic gist, though, is what we would call echo cancellation, which is I want to to sort of zero out the copy of my signal while I hear the full copy of your signal. And I'm going to rely on the fact that I know what I transmitted electronically. And so I can essentially use my transmission to cancel itself out when the echo comes back. So that was the full duplex problem. Then the next problem to solve is, okay, we actually want 2 transmissions going in each direction. What do we do there? And the article I read about Edison, and I'll admit I cheated a little bit because I didn't know how it worked and I was curious myself. I asked the same question. The article I read said that essentially they used 2 different polarities of the battery. And so essentially one of the transmitters was positive polarity, the other was negative, and then they essentially played a trick where my sounder would only be triggered by the positive polarity signal, and it would essentially not sound on the negative, and then my neighbor would have the opposite. And so,
very clever.
And it
very simple. I thought for sure you were going to say something about frequencies.
Yeah,
but
not yet.
We're way off of that.
Yeah,
here. Yeah.
This was still in, I guess, what we would call like DC or baseband, where it's just on off, electricity flowing or not. But essentially now they had 3 states, which was, on positive, on negative, or off, and so that allowed them to then kind of combine these signals. I honestly don't know, like if we have an on positive and on negative at the same time, that seems like a problem. I don't quite know how it worked, but maybe it relied on the fact that your duty cycle was less or something like that. So
and this fundamentally limited the operators to 2 on each side. There's no way you could do more because this multiplexing technique really just only allows for 2 simultaneous signals.
Exactly. They'd run out of degrees of freedom. There was no way to generalize this to like 4, 6, 8, 10 or something like that.
Yeah. That's coming later though.
That's right. So
just wait.
So Edison did this, and and then he moved on to light bulbs and other things. Probably worth talking about the next step, and then we might be getting kind of close to what we want to do here. And so the next technique, I don't know who started doing this, but there was a guy we've heard of who was working on this. His name was Alexander Graham Bell. And his technique was what you called out as frequency division multiplexing. And so again, multiplexing, we're putting multiple signals in one place. But the idea here was, what if instead of my signal was just being like electricity on or off, what if it was actually an oscillating wave? I tend to think of picture the sound coming out of a piano when you press and hold a key. And what if the transmitter next to me had a different frequency or a different pitch or tone of oscillating wave? And a trained musician can hear 2 piano, a chord, 2 keys being played at the same time, and they could hear okay, there's 2 different notes being played there. And you can build electric circuits that can filter these oscillating signals out and select them one by one, even if they're all sharing the same medium in combination. And so we can have multiple transmitters, each with their own frequency. And when they're transmitting, they transmit that oscillating frequency. And when they're not transmitting, they turn it off. And then on the receive side, we have filters that, based on which frequency, each one's tuned to a certain frequency. And when that frequency is active, it then activates its sounder. And when that frequency is inactive, it then does not activate the sounder. And so you could actually combine potentially a large number of separate transmissions onto one wire, as long as the wire could hold all of those different oscillations in superposition. And this is what we call the bandwidth available in an analog state, which would be, how many different frequencies can you actually handle at the same time?
Yes. And
of course, the second part of the story is that while he was working on that, and it would have totally worked to make, 8, octoplex telegraphy, he heard his own voice being carried through this system, or maybe his partner's voice, and realized that they'd made something much more interesting than an 8-way telegraph. They'd actually made an electrical system that could carry human voice over a distance.
Well, look at that. Once again, we shipped something to production that we had hoped would allow for 8 telegraph operators to run at the same time. And instead, it turns out it carries human speech.
You can talk to it. Yeah. And so
what was the mechanism that picked up and transmitted their voice? Surely they didn't have microphones. The concept didn't exist yet.
Yeah, I don't think they did, but I haven't looked into that. But yeah, I would assume there was something that was just causing enough vibration of the apparatus, and then that vibration, who knows all the humming and sounds that were coming out of this as he was working on it. And yeah, somehow just maybe even just could hear it changing in some way as he spoke and realized, there's something here.
I have to imagine that it went something like this. He's working with these wires and he shocks himself and screams and says a curse word. And that it's loud enough that the clicker moves a little bit in response to his vocal, in response to the sound waves. And then it comes out the other end and the operator on the other side can hear it. And therefore, the first telecommunications were a profanity. This is my guess. This is the story I choose to believe.
It seems totally reasonable to me. I'll grant it to you. That can be our unchecked fact of the day.
Canonical history now.
That's right. And so, of course, there was a whole lot of work to actually make that into a thing that could carry intelligible human voice and carry it over a distance. Just as groundbreaking as the telegraph was, that you could send these taps over a distance and transmit messages, information, this ability to speak and be heard across a distance beyond shouting distance had to just be mind blowing.
Oh yeah. Total huge step change in the technology.
Absolutely. And so with that, the telegraph stayed important, but its importance shifted really, I think, to business operations or very long distance messaging, official correspondence, essentially what you would send a postcard to do. And the telephone quickly became the way that people would talk to each other, first in a local area, and then eventually over those same long distances, including around the world eventually, that the telegraph could reach. And then that probably took till late 1800s, early 1900s. And the American Telephone Company, which became the American Telephone and Telegraph Company, when they started figuring out how to make their telephony systems also carry telegraph signals, something we'll talk about later. And essentially,
a little backwards move.
Yeah, exactly. And sort of the voice system became the reason people built communication networks. And in the US, it was a company called AT&T that did this. And in order to carry more voice conversations over longer distances at a lower cost, they developed a whole set of technologies, and those technologies ended up being very important for data communications as well. But it's probably worth saving that conversation for another time.
Yeah, it definitely is. But I before we move too far away from the telephone,
okay,
and I want to ask you a question, but stop me if this goes beyond your knowledge.
Yep.
And that is that we and I already pushed you a little bit too far on Edison's quadruplexing technique, like what were the physical components that he used to do that. We had some ideas on that. What were the physical components that Alexander Graham Bell used to create oscillation in electricity?
Oh, like for the frequency division multiplexing.
Mm-hmm.
I don't know. Yeah, I mean,
maybe he stood there with a wire and just like shook it really fast at a certain
go.
speed. I don't know.
I
mean, somehow he had to generate this because was it alternating current, you think, or was it DC?
I think it would have had to be some type of oscillator. So I don't know if it would have been. I mean, so yeah, it would have been a form of alternating current. Some type of circuit that was generating, presumably a sine wave. But I don't know what types of circuits he was using to generate those. I don't really know what the technology of the day.
It really was a big technological leap, right? Because not only does he have to generate these signals with an oscillator, but he also has to be able to precisely move that oscillator at a frequency that is both constant and distinct from the neighboring oscillators, and he has to do 8 of them or some number of them at the same time.
Yep.
And then on the other end, he had to invent technology to actually filter out the signals that are not intended for your receiver.
Right.
But boy, man, this was a huge amount of technology he had to develop.
That's right. Yeah, and I don't know how much was known in versus what he had to do himself, but you're absolutely right. You're building oscillators, you're building some way of combining these signals without them really affecting each other, and then all the filters on the other side. So yeah, it was pretty advanced, electrical circuit design for the day. And yeah, I kind of wonder when he switched to telephony, if in a way it got easier, because now the oscillator is the human voice, and you just had to find a way to capture that, transmit it, and then reconstruct it on the other side.
Yeah, because we haven't gotten to, and I don't know if Alexander Graham Bell ever got to multiple voices over the same conductor, but We will talk about that later.
That's right. Yes.
In a future episode.
Yeah, for sure. That's where it went. The Bell Telephone Company, which then became AT&T, did and develop all those technologies. I don't know what hand he might have had in it though.
Question for you on that. Was the telephone system able to use the same single wire architecture that the telegraph system had been using?
So my understanding is over any meaningful distance, the quality was too low with single wire, and so they did have to go to dual wire at that point just to have a nice clean circuit.
Yeah, I wondered about that because I mean the fine-grained nature of these signals is just so much more sensitive than the clicks that you were trying to get with the telegraph.
Exactly. Yeah, if you think about the information you're sending, the on-off, you could put a lot of noise on that and it would still click on the other side, but voice just had a lot more subtlety to it. And so
the noise would swallow up the voice if you weren't clean enough, right?
Yep, exactly.
Okay. Should we pause it here?
I think we should. I think there's more to talk about, but I think this is a good place.
Why don't you shoot us a little teaser for what's coming next? Just a brief, just enough to whet my appetite.
All right. So I think what comes next, and actually this is a pretty good stopping point, because so far we've been talking about ways that human beings could operate the two endpoint devices to transmit and receive information. And I think the next phase is, how do you get rid of those pesky human beings and make systems where the machines can talk to each other? And once you do that, off you go.
So now you're talking like machines talking to each other, or you're saying that a human can use a machine to talk to another human without paying an operator to do that for them. Is that what you're saying?
We'll start there, which is humans using machines that have the brain of how to communicate as opposed to the human having to know Morse code and so forth. And then from there, we'll figure out how to simplify and reduce the job of the human until we can finally eliminate them entirely. And by that point, we're talking about computers. So we'll find our way all the way to computers next time.
I'm trying not to interpret that we're going straight from voice telephony to Skynet, eliminating the humans.
It's the natural trend of all technology, isn't it?
We're still determining that, but yes, as far as Hollywood is concerned.
I was gonna say, as we know, we don't know how many episodes it'll take us to get there, so no promises on that.
Yes, it is. Yeah, that's right. I would say to be determined, but honestly, it is to be discovered as we go. Right. In much the same way this technology was discovered, we are discovering how long it will take to talk about this technology as we go. So thank you so much, Shane, for your time today. This was, as usual, totally enlightening for me, and I really appreciate it.
Yeah, you too, Dave. Thanks a lot.